Yeah, it's a pleasure today to welcome Bénédicte Cenki-Tok. I will give a short introduction. So Bénédicte is an associate professor at Montpellier University in France, and she's currently a European Union H2020 Marie Curie Research Fellow at Sydney University. She graduated from a PhD in mineralogy at the University of Bonn in Germany before working successively as a postdoc fellow in Strasbourg and the UK. And then she moved to Bern, where she worked for 4 years as a research and teaching assistant. And she now has 2 decades experience in teaching and research as a hard rock geologist. Her expertise allows her to tackle 2 major research questions in earth sciences: how mountains build and collapse, and where to find critical minerals that are essential to the development of the green technologies at the core of emerging low-carbon societies. And so today, Bénédicte will speak about critical mineral geosciences, renewables, and sustainability. And I am really curious to know what is hidden behind this title. So Bénédicte, we are listening to you whenever you are ready.
Thank you very much, Marion and Alannah and the entire Ore Deposit Hub for hosting me today. Good evening if you are sitting in Australia or even in the US. Good morning if you are waking up in Europe. I'm really grateful for this opportunity to tackle this very large question about critical minerals, geosciences, renewables, and sustainability. Why do we need to create a sustainable future now? And what is our role as mineralogists, petrologists, hard rock geologists to answer this question and to contribute to this very important question? To me, I believe that one of the most important challenges we are facing as humans in the next century is climate change. We've seen in the past months that there will be, and there are probably others as well, but the topic in which we can contribute is probably climate change. It has been mostly the effect of an anthropogenic, a drastic increase in anthropogenic CO2 in the past century, and this has drastic consequences on our planet and the environment in which we humans are living. And this is mostly due because we have been using as a principal source of energy fossil fuel, which emits CO2. Actually, the drive behind, and there will be only one slide on that, and this is one very general thought, is that the population of the Earth is increasing drastically as well. Back at the beginning of the 19th century, we were only 1 billion on the planet. We are close to 8 billion in a couple of years, and this is not meant to stop. And everyone would like to access to a certain lifestyle, and for this we need energy. One of the solutions that has been proposed in the past decades is to turn into renewable green technology, which does not emit CO2. It means that we can use the power of the sun to transform them into electricity via solar panels, or use the power of the wind to transform into power using wind turbines. But this has a consequence as well, that I guess in our community, we might be quite well aware, but I'm not sure that in the general public is so much informed. And we need to spread the word that turning into renewables will have drastic impact on the amount of raw materials that will be necessary. In this diagram, which is a prediction for the production of concrete and steel in billion ton in y-axis versus time here in x-axis, we are sitting here in 2020. This is a prediction made by Olivier Vidal a few years ago already. And even for such basic raw material like concrete and steel, it is predicted that whatever scenario we'll take with renewables, either this full square or empty square, I will not enter into details. The production will be at least 2 or 3 times more in the coming decades. And this is the same for aluminium, glass, and copper. For example, this hole is one of the largest copper mine in the US, which is like 3 times 1 times 1 kilometer. And as a scale, these tiny little dots, do you see my mouse here, this arrow moving over here? This tiny little dot at the point of my arrow is this huge truck with those drivers here as a scale. And in this hole that has been dug in the past 100 years, there has been extracted 6 billion ton material, 18 million ton copper. And if we turn into renewables, for example, we'll need 7 to 15 of these holes in the next 10 years. And this is only 100 years of work. So this is incredible. This amount of material we will need is enormous. The other aspect of turning into renewables is that we will increasingly have a variety or necessitate a variety of chemical elements compared to a few hundred years ago. Back in the 18th century, humanity was using only a handful of elements like lead, zinc, copper, and iron for its technology. But currently here, on all the high-tech devices we have, the renewables, we are tapping into almost every cell of Mendeleev's periodic table, with almost like 50 elements needed for the high-tech devices and renewables, and often in tiny quantities. As an example, this is a very fancy car, which I cannot reveal the brand, an electric car, and for the different parts which are quite specific to electric car, like the hybrid electric motor or the battery, we need elements like neodymium, praseodymium, lanthanum, which are rare earth elements, and often they are very diluted as well in these components. Just a short side story. Recently, I popped in a Zoom meeting of a clean tech startup meeting for the city of Sydney, organized by the city of Sydney. And I wanted to tackle these questions that, oh, we turn into renewables, it's really great, which I have nothing against. And I tried to ask the different presenters and different CEOs about what is the provenance of the critical minerals, and absolutely had no feedback about that. So I think this is still something we need to spread the word about, that we need a lot of raw materials and as well a variety of materials, which is unprecedented. So I'll have a short break now and like to leave you with this thought from Olivier Vidal in his Nature Geoscience paper a few years ago. If we shift to renewable energy, we will replace a non-renewable resource, which is fossil fuel, with another one, metals and minerals. And even writes in his text, humankind faces a vicious circle. So can we unlearn renewables to make them sustainable? I may not have all the answers in this talk, and there is probably more questions and answers in the following slides, but I would like to show you in a quite humble manner how I would approach critical mineral geosciences in this context. So let's now first and have a look at some definitions, because we are using the terms critical minerals, rare metals, critical metals, and strategic elements. In this diagram on the right-hand side, shows on the x-axis the economic importance of some chemical elements versus supply risk in x-axis. This is a criticality matrix which has been published by the European Union already 10 years ago. And now I guess they are starting working on 3-dimension diagrams that involve the environmental impact of this, but I haven't found any yet. So one of the elements which are most critical and important for our economy in the top right quadrant of these diagrams are rare earths, the tiny elements we needed in this very fancy electric car. And I'd like to draw your attention to some other elements like germanium, gallium, and indium, which have zinc affinity, and I will reuse a few examples in this chemical system in the next slides. From a different perspective, the Australian perspective, this is a flip chart, a flow chart indicating which elements are the most critical for Australia, according to Geosciences Australia. Number 1 are rare earths, same as for Europe or the US. Number 2 and number 3 are gallium and indium, which have zinc affinity. In terms of supply and provenance for the European Union, where do the critical minerals used in the technologies in Europe come from? What is most striking is the largest pie over here, which is the most colorful as well, corresponds to China. It means that many elements that we are using in Europe for the technology in Europe and for very different kind of elements, these very different colors comes from China. Like 95% of the rare earths come from China, 80% of gallium here in yellow, germanium in orange, 67%, and so on. To come back from a slightly different perspective, and I'd like to open up a sideline as well, is what strikes me is this tiny little pie here in Australia, whereas Australia has a huge mining potential and for critical minerals as well. This talk has been designed slightly in the past month for Australia, so I'll take few examples as well from the Australian geology and the Australian context to illustrate some ideas. For example, Australia has a huge potential in rare earths. These are those red dots that you can find almost all over the place here in New South Wales and Victoria, in Western Australia, as well in these Northern Territories, which is one of the most promising rare earths mine with RF rare resource taking that on. I'd like to draw your attention as well on these yellow dots here in Western Australia. We show a huge potential for lithium. A more general manner, in which kind of rocks can we find critical minerals? This is not exhaustive, but many of the critical metals and minerals can be found in magmatic and metamorphic rocks. For example, this on the right-hand side, this is a beautifully crystallized magmatic rock with leucochromatic minerals like quartz and feldspar and shiny purplish minerals, which are micas containing lithium, lepidolite. These are pegmatites from the Yunnan project from Western Australia. On the left-hand side is this beautifully banded low-grade metasediment from Mount Isa in Queensland. And in the middle of this slightly banded foliated rock metasediment, there is a centimeter-sized shiny layer, mostly composed of galena and sphalerite, which are zinc and lead sulfur, that may contain germanium, gallium, and indium. The bottom line is that in this kind of rocks, mineralogy is the key, not only to explore, but as well to better recover the metals, the critical metals that are located either in crystal lattice or maybe in separate phases. Most of the work that has been done now in order to understand where to look for critical metals and critical minerals is based on machine learning approach, combining a large data set, finding correlation vectors between base metals and critical metals. For example, one of the large databases we have in Australia is the OSNACA database, and this diagram shows, the scatter plot shows the correlation of zinc concentration in ores. This is a log scale in x-axis and indium in ppm in the y-scale, and this is as well a log scale. So the first observation is that these concentrations are all over the place. Note that the crustal abundance of this rare metal is 0.1 ppm, whereas byproduct grade is 1,000 times more. So a lot of effort has been made working with this database and yielded this wheel of companionality that you must have seen already, indicating that in the middle here, dark blue circle are different base metals, for example, zinc. And when we read that diagram towards the outer circles, we can find the different rare metals that can be associated or found in association. For example, with zinc, we can find germanium, indium, gallium, silver. But to me, in order to be much more resource efficient in looking for these critical metals and minerals, I believe that one of the major questions that we need to tackle is what are the concentration processes of rare metals, so that we can maybe find proxies or vectors that are much more straightforward to go to find them. I'll use an analogy. For example, germanium is a concentration in the continental crust on 1.5 ppm, and it is found and exploited in traces in zinc and coal deposit between 3,000 and 5,000 ppm. When I arrived in Sydney, like 1.5 years ago, Sydney is maybe 5 million people. So let's say that 1.5 ppm corresponds roughly to a French family. I arrive in Sydney, I want to find a French family somewhere. So what do I do? If I just drive around and try to find one family, it would be quite difficult. Better to find a way of concentrating these French families so I can make better friends, so that I can get maybe like 100 families, which would correspond to this kind of concentration. So I just need to know where the French school is, and I know the French neighborhood. I just need one proxy. I just need to find one thing. So using this analogy, I believe that answering this question, what are the processes for concentrating rare metals, will help us being much more efficient in finding these and recovering these. Now in the next slides, in the next 10 to 15 minutes, I would like to unfold a few examples which are, I apologize, probably not exhaustive, but I believe are very important facets of critical minerals geosciences, from the small to the large scale. And I believe many of you in the audience must have some complementary examples to share as well, in order to understand what are the concentration processes of rare metals. For that, I will use the example of germanium, because I've been working on this theme for a few years. And this is a PhD project that has been funded by the French Geological Survey and ended last year. I would like to thank Alexandre Grosjean, who did a really amazing work in this framework. And the next slide, and for the paper he has just published. And by the way, short announcement, he's looking for a postdoc. So in case you have any opportunity in your lab, please don't hesitate to contact him or myself. So go back to germanium. Germanium can be found in various types of contexts, and I will just focus now on orogenic veins. From a mineralogical point of view, germanium can be found either in the zinc sulfur lattice, which is sphalerite. Please note the 200 micron scale bar. So this is millimeter scale sphalerite, which can contain up to 1000 ppm in germanium. But we can find this rare metal as well in tiny minerals. This one over here, please note the scale, this is 30 microns, so this is less than 100 microns. This is a germanium-bearing silicate carbarite and a germanium-bearing oxide, brunnogerite, and these minerals can be concentrated up to 78%. So they are really mineral phases that are highly concentrated. So how do we understand how nature concentrates this rare metal at sample scale? Let's first have a look at this top slide. It's an optical microphotograph of a sphalerite. We are in orogen, so there is metamorphism deformation, and this dashed white line, it represents the latest foliation recorded in the area. The bottom picture is the very same area, and this is a grain size map, an EBSD grain size map, indicating that we have coarse grain here in brown, more than 100 micron, and fine grain domains here in blue. Germanium minerals, highly concentrated, are exclusively located in precrystallized domain. This colorful picture on the top of this slide is the very same area as well, but this is a misorientation map, an EBSD misorientation map. We found again this large grain here in bluish, greenish, homogeneous color, and these very patchy fine grain domains, indicating that each neighbor has a very different misorientation than its neighbor. From the cross section from B to A, we show that in the large grain, misorientation varies smoothly for a few degrees up to 20 degrees, indicating that sphalerite deforms in a plastic manner. When we enter the fine grain domains, the misorientation of each grain to the other jumps sharply from 20 to 60 to 20 to 50. And this shows that this processes is dynamic precrystallization, which leads to these fine grain domains. So now that we have a look at the texture, can we have a look at the chemistry? First of all, in a qualitative manner. On the left-hand side, this quite colorful picture is a misorientation map as well. And if we zoom in this bottom right part of this sphalerite, we have bluish concentration, we have low concentration, a few ppm, and up to high concentration with these yellowish domains, up to 8% in concentration, and the higher concentration are localized in the recrystallized domains, for example, over here and down here. Let's now have an idea about the in situ chemistry of this. This is again a sphalerite map. On the left-hand side is a grain size map with now the coarse grain in gray and the fine grain recrystallized grains in red. If we zoom into this area, the coarse grain, the color code is changing because this is optical microphotograph. The coarse grain here in dark red have concentration up to 500 ppm germanium. And if we just move a few hundred microns away in the fine grain recrystallized matrix, we have less than 10 ppm. So there is a strong chemical heterogeneities that are linked and associated to strong textural heterogeneities. As geochemists, we love doing these diagrams, this correlation diagram between different chemical vectors. So this is one, copper here in x-axis in ppm versus germanium in y-axis. This summarizes that the coarse grains here in brown and white squares have concentration of a few hundreds of ppm germanium, whereas the recrystallized matrix down here are depleted in germanium. If we want to make a mass balance at this sample scale, we have to take into account this yellowish bubble, which are germanium minerals concentrated up to 78% germanium that would be up to the roof on this scale. Just one slide to show you that we've worked, his work on a large amount of rare metals associated to zinc as well. And these are all the literature data available for sphalerite that Alexandre has compiled. So this is copper in x-axis in ppm. This is log scale, large variability. Germanium in ppm in the y-axis, log scale as well as large variability. The process we've highlighted associated to dynamic recrystallization explains this trend here between the bluish to purplish trend. It means that to explain this large variability, there must be some other processes as well playing a key role in explaining the large variability of germanium and rare metals concentration in sphalerite worldwide. So I guess if you ask the West question, we can find the right tool to explain this concentration and where to find them, whether it's in the ores or in the tailings that I will talk about in a few minutes. So the process we've highlighted and the way we're explaining it is that for this model of natural concentration of germanium reconcentration remobilization is that we have a vein which emplaces quite late stage of the orogeny, a sphalerite vein here in dark green. Then we have a late deformation stage that recrystallizes locally the sphalerite. And during this process, everything happens as if the germanium, which was in the primary sphalerite, is expelled, these red arrows, and concentrated in those tiny germanium-bearing minerals, highly concentrated, leaving behind this pale blue sphalerite matrix, which is depleted in germanium. These conditions, the thermodynamic condition associators are probably Greenschist facial condition under oxidizing fluid, but I will not enter too much into detail here. Is just to highlight that one of the processes for which nature can concentrate rare metals is dynamic recrystallization associated to mountain building. Just one slide to show you that I believe that this process can happen as well in different chemical systems. This is one slide from Asma Jedi PhD thesis. She finished in Montpellier last year. She worked on carbonatite from Algeria. Carbonatite is one of the main reservoirs worldwide for rare earths. And what she has found is that in this huge apatite crystal here on the left, so the scale, this is 2 millimeters. So this is a millimeter size apatite, which has a few weight percent rare earths in its structure. But if you zoom in here, this yellow square, we see that there is a apatite consuming reaction that forms this pinkish mineral, which is britholite, which is way more concentrated in rare earths. And this is not a magmatic process. This is a post-magmatic, low temperature, metamorphic hydrothermal alteration. So this late remobilization has concentrated rare earths in that case as well. So it's maybe food for thoughts. There has been some other studies showing the mobility of elements, various elements during prograde metamorphisms. For example, Pitcairn et al. Showed 10 years ago in the Autogoschist in New Zealand that during Barrovian metamorphism, we have metals coming in and out depending on the system, depending on the sulfur stability, whether it's spirit or pyrrhotite. Indium as well. presents a large variability in orogenic zinc deposit. For example, in this study from Lockington et al. A few years ago, they have analyzed indium here in ppm in y-axis in different orogenic deposits in Australia and the Scandinavian Shield, and they have found large variability of concentration as well, associated to the formation of indium-bearing minerals like rockasite, which is a copper and indium sulfur. 2 slides to tackle the large scale. I will not dwell too much on this topic. My heart is more of a hard rock geologist, so I would say tectonometamorphic evolution, having an idea of the large scale, the large structures, the geometry, whether it's like a brittle or ductile structures, is always a good idea to know where you are going when you are looking for deposits. But the second large scale approach, I would like to share only one type, and this is very early thoughts about the insight of rare metals being pegmatite using thermomechanical models. Temperature is one of the main parameters influencing formation of ore deposits in general, and maybe a little more when we think that critical metals are very often located in magmatic and metamorphic rock. So this is a screenshot of one thermomechanical models that I ran a few months ago. This is a box about 100 kilometers in depth and 360 kilometers in width. And in this model, I allow the crust, which is here in orange, which could be, let's say, unfavorable facies condition, and allow the crust to experience important metamorphic phase change, which is like partial melting, this yellow curve here in this PT diagram. So this transforms into a pegmatite. Bring back to the pegmatite, this can be LCT, lithium, cesium, tantalum pegmatite, which usually is the product of the partial melting of the crust. But at high temperature, and the crust is also allowed to transform into granulite, which should be a strong garnet product in rock. And if this one starts to melt as well, this can yield to the formation of heavy rare earths being pegmatite, like this one here we found in Central Australia, which is fergusonite, a heavy metal rare earths, heavy rare earths bearing pegmatite. And usually we explore more for either or type of pegmatite, but this model maybe can give us some insight that depending on the protoliths and depending on the thermal conditions, we may look for both maybe in the same place. So this is very early thoughts and stages that still need to be tested that I wanted to share with you today. If you want to know more about these thermomechanical models, I gave last week an entire talk about this kind of thermomechanical models to explain the formation of high temperature, ultra high temperature terrain within the IGCP supercontinents and geodynamics virtual seminar series. So let's now go back to and broaden our vision as well about an idea about sustainability in the supply of critical minerals, and now how we can apply the lesson learned from the hard rocks we are looking at. So looking at tailings is starting to be a very good idea in order to transfer, unlock critical minerals that are maybe have been maybe piling in the mine waste. So how would I do that? I would go back to this example. In Australia and in very different countries, there is 100 years of mine waste just piling, for example, in zinc mine. If I go to Perilia in Broken Hill or Glencore in Mount Isa, which is I'm trying to do, is to pick up some mine tailings and look for gallium, germanium, and indium in these ones. If the lesson learned from the rocks I've studied before, if it is true, then I would just take two types of tailings. I would take a fine-grained rock, a fine-grained tailing, and I would expect to have germanium, maybe gallium and indium, are located mostly in tiny minerals, which might be much more recoverable and extractable by physical means. But if I have a coarse grain sphalerite, I would more expect germanium to be located in the lattice, so that would need more heavy hydrometallurgical processes to process. So the question on the top of this slide must be, maybe is a bit provoking, but I believe we can just ask these questions. If the process for concentration of critical minerals are different than for base metals, so what kind of tools would we develop? First time I presented these ideas was a year ago in Peckham in Auckland. Travis Murphy, who was in the audience, shared some slides from his PhD in Mount Isa in George Fisher Mine, owned by Glencore, and he did report a large variability of grain size in these zinc ores. Finally, and I think this can be transformed to many terrains around the world. The different colorful squares here correspond to a zinc resource in Australia, and ores, and probably mine waste as well. So to me, whatever the initial process that has formed this zinc resource, all are located in these colorful patches, which are orogens. And orogeny means the rocks have suffered metamorphism, deformation, or maybe enjoyed. But the bottom line is that many processes must have occurred to reconsecrate, remobilize on the rare metals in orogenic terrains. And many of these are located not only in Australia, but in many places and where that have been affected by supercontinent formation, like in South America, Africa, Scandinavian Shield, Canada, and so on. To wrap it up and take a little bit of a broader approach and back to some themes that are a bit more far away from my core expertise. There is a lot of question as well and proposition in this presentation, but I believe what is 100% sure is that if we continue mining in a traditional manner, we will for sure encounter the supply shortage and the environmental crisis in a few decades again. So let's start now to share some ideas about how we could do it a little bit more sustainable. It's not only important for the planet, but it's important as well to protect the people. Maybe most of you are aware of the lawsuit against Apple, Google, and Tesla in the recent years, because most of the cobalt, you cannot fly a plane without having some cobalt coming from some places in which child labor is still very much in use. So it's not only important for the planet, it's important to protect the people as well. Of course, there are some really good practice example, and I'd like to share one from the high-tech project funded by the European Union, which was led by the British Geological Survey, and my colleague Catherine Goodenough, who may be in the audience. She must know much more than me on this aspect and work on this project, for example, with Makongo, which is an advanced stage rare earth project and really takes to the heart the social license to operate and the responsibility and involved with stakeholders in their practice. As a kind of conclusion, working toward a conclusion, I really love sharing this slide, which is a little bit old as well. It's one of the first projects funded by the European Union on the integrated management system for rare earths. This is a URARE project. And integrating these different aspects. So first thing I noticed in there is that we need to be very, very humble with what we can do. As geologists and hard rock geologists, we are just somewhere here in this orange quadrant. And if you want to tackle the problem in an integrated manner, we need to work with engineers who will help us make a better utilization of tailings. But we, as mineralogists and petrologists, we will know, we will help them as well. So it's like a win-win combination. It's the same for optimizing beneficiation, finding novel extraction technologies. There will be some chemists and physicists working on developing better end products and better design of these end products, and maybe find some replacement materials. But we need to talk to each other from a very early stage to make it more efficient. And of course, we need to involve people who know the economy and what's worthwhile, and people who know the different legislation. So I really love sharing this slide. I think Catherine was leading this project as well. And what's important is creating a synergy with critical minerals. Geoscience is important. We shouldn't think about that, and we shouldn't deny that. And mining is probably unavoidable, but we can think in terms of mining locally, in urban mining, recycling, sustainable mining, but working with engineers, chemists, finding substitute and recycling, thinking about the environmental impact, finding new efficiencies in ore processing, informing policymakers and the general public. So to me, the bottom line is creating a synergy and talking in a humble manner to each other towards solution. One last slide on recycling, and I'll refer to Olivier Vidal's talk, which is available on YouTube, and showing what's the importance of recycling for copper. So this is a prediction through time. We are here in 2020, and this is a production, and the demand for copper will increase. But in order to get the primary production here, this is this purple curve, kind of stable, let's say in 2 or 3 decades. It's absolutely essential now in 2020 to build the wind turbines in a manner that after the lifespan of this wind turbine is gone, like in 20 years, we can get this material out and recycle them so that this red curve increases and takes most of the and results in most of the productions that we need to respond to the demand. So I really invite you to look at Olivier's talk on this YouTube link. Is really a great approach. Finally, bring this idea into the circular economy, which is what we are thriving for. This one is taken from the Ellen MacArthur Foundation. I'm not talking about biological materials here. All this left-hand side is green material. It's way beyond my core expertise, but where we can work is in this mining and technical materials. And we have a role to play in this circular economy in terms of finding the resource, but not only in terms of mining or traditional mining, but in terms of better supply, and in a large sense. It means like looking at tailings, finding with our knowledge better ways of extracting, recovering, and beneficiating these minerals from the ores or the tailings or the wastes. Thank you for your attention. If you're interested in the broader view I've shared here today, I refer you to the conversation article that I've written a few months ago in the conversation, and there is another one last month, which is much more focused on rare metals concentration. And thank you for your attention.
Thank you very much, Bénédicte. This is an amazing talk and really nice overview of all of these different key aspects working towards a sustainable future for especially for our critical metals. I see there was earlier quite some discussion going on to do with the recycling of the different metals. But I do have a first question for you here, Bénédicte, and that is to do with the potential to get something like germanium from fly ash or red mud, and if there is any potential there. And that question comes from Nikal Dawan. Do you have any comments on that?
No, I think I haven't thought about that. So recycling from which material?
Fly ash. So like I don't know. From my experience here in the University of Bern in Switzerland, I know there's a group that's working on we have a lot of incinerator plants, and they do produce fly ash, and I guess there is quite a lot of zinc in there, so maybe there is some potential for something like germanium or the other elements you mentioned, or in red mud. That was the other question.
Yeah, I haven't thought about this specific case, and I guess there is a lot of specific cases that can be like erosion, but I think the workflow would be quite similar. I mean, we use you first have to image these particles and look at the chemistry, the texture, and trying to find not only the concentration as bulk of this fly ash or whatever, but understand the processes of where they can be located and in which minerals and this. So I'm more kind of, to me, it's about finding the red lines that can be applied to different contexts, whether it is an ore, whether it is a fly ash, whether it is a tailing, whether it is like in this chemical system or this chemical system. To me, it's important to find kind of a workflow that could help us in a efficient manner to answer the question whether these rare metals are concentrated or not. And to me, as I'm a mineralogist and a petrologist, and this is the first time I really think we can contribute with the tools we've been using for a long time in our core expertise, and share that and use the same workflows, looking at texture, not only bulk chemistry and global data, but looking specifically at texture and in situ chemistry to understand processes that just more like saying, oh, it's concentrated or it's not concentration. So I'm well aware that I'm answering around the question because I've never thought about that.
Yeah, that's no problem. And thanks very much for giving that answer. And I would refer, if anyone's more interested in particularly the red mud and like bauxite story, we do have another talk this afternoon, which is exactly on that topic. So by Emir Didi. So please do check that out if you're more interested on that line. And with that, Marion, do you have another question coming up there?
So we have a question from Catherine, which unfortunately said she could not really unmute herself. But I'll ask the question.
She said now she can.
Okay, sorry, I didn't follow that. So Catherine.
Sorry, I'm here now. Would you like me to ask it, Marion?
Yeah, sure, go for it.
Morning, Bénédicte, and thank you for a really good talk. I just thought that was a really good description of how the major metals like copper and zinc are potentially, those deposits are such great sources for things like germanium and indium, but obviously they're often not produced as byproducts. A lot of mines aren't producing them. What do you think we can do as researchers in this area to try and encourage them to look more at producing byproducts like that?
So I confess I haven't really tackled the question of the economic viability of looking at these minerals as byproduct or not. But I would say that at the first stage, and this is what I'm trying to do in Australia, is to first look at mine tailings. So it would like at the first stage look at the potential for mine tailings. So this could be a byproduct, but not only at the end tailing, but through the entire process of the chain of getting what the mine needs to get out, and trying to understand at which stage maybe they lose this critical metals. They can be maybe more or less easy or costly to integrate and to get as byproduct. But I believe the first thing would be to understand the process as and then think in terms of tools to bring them and get them out in terms of byproduct or not. And I may be a little bit optimistic or idealistic, but at some point, we need to not only think in terms of economic viability, and I think it is our duty as academic, as we do not have this economic pressure, to propose maybe advantages to the companies, showing that maybe they could try to engage in R&D and valorize these products and maybe first look for these products, and instead of just importing them. I think in Australia, there's a huge potential for many critical minerals, and they're still importing from China. So, yes.
Thanks, Bénédicte.
Thanks. So yeah, it's a broad question, but you said you're not really in contact with the company, and in the same time you presented at the end of your talk that it should be a sort of a big group working all together. So do you, like yourself, plan on integrating more of the companies to your work in the future, or how would you like to work with this project on tailings with them? I mean, to help the things work better.
First of all, we have to be very, very humble. It's very difficult. I mean, I'm trying to engage. Even it's a side answer as well. I'm learning thermometrical models in the past 18 months, and it takes such a time and work to try to communicate with our colleague doing mostly the same thing and try to understand each other. Now on the tailings project, I'm working with a low temperature geochemist, and we still need to learn how we can talk and understand each other in order to tackle. So it's quite ambitious, I guess, and it needs some cognitive humility to try to understand how the other person works. So to answer the specific questions, I would like to apply and test the workflow I've presented here that we've shown for Germanium. I believe it can be important for rare earths as well, but as well for PGs in ultramafic tailings, as this very simple workflow, instead of looking at the bulk data, but looking in terms of processes. And once we understand the process, and if it is reproducible, whether it is a tailing from a zinc mine or of a IOGC copper mine where we could find rare earths, or ultramafic rock, trying to locate the resource, first of all, with my core expertise, and then try to open up. We need to build a large working group, and this takes time. Together, the right group which can work together the funds. So we need to work step by step. But I think Catherine, who is in the audience, already has the European experience of gathering quite large experiences, people from very different backgrounds in this common effort. But this is still lacking in Australia, and there is everything to do over here to transfer as well our European experience here.
Nice. So good hopes for the future.
Yes, there is amazing potential. Yes.
Great.
Alannah,
I have another question here. One for me to read out from. I hope I pronounced your name right. Christoph Fulton. So they say, so metamorphic processes, you showed us that we need them to kind of to concentrate the germanium in the sphalerite, but what processes can initially put the germanium there in the first place before we have this dynamic recrystallization?
So about the source of, for example, germanium, this is a question we had. I can answer only quite specifically for germanium. in this context, it was in the Pyrenees. We had a lot of organic matter which sediments around. So we believe it's like even primary early phases of metamorphism which have reconcentrated germanium from the metasediments, which can be rich in organic matter because germanium has an affinity with organic matter. Some people argue that it can come from some surrounding granite as well. In this very specific case, we haven't performed germanium stabilizer work which can help decipher the different sources. So, but the question of the source is always here. So it's a specific answer for germanium, but I haven't really digged into that far in the different contexts.
Okay, great. No, thank you. That's really interesting to see there's different potential sources there. Yeah. Okay, Marion, do you have another question there?
Yeah, we have a question from Romain Millot. I think, Romain, you can ask your question out loud. You're unmuted now.
Tell me if you can hear me.
Yes.
Yeah.
Okay. Hello, everyone. Bonjour, Bénédicte. Thank you for this very interesting talk. I have more a comment. It's not really a question. I think we have also to consider a non-conventional resource for minerals, for metals. I mean, we can get mineral resources from brines, and we can produce locally those metals in order to reduce the CO2 budget for this production. So it's also a good alternative. But it's just a comment.
Yeah, I haven't taken this question in detail, and I know I think you've worked on the lithium bearing brine from Europe, so I guess this has a huge potential as well. But I confess I haven't really digged into the question as well. So of course there are many efforts in different manner, and I've been non-exhaustive about what's possible. But I believe what's important is our intention.
A lot of innovation and disruptive technology that in order to extract several metals from brines. So it's also very interesting.
There was a question, I haven't quite heard the end of the sentence.
I just mentioned that there's a lot of innovation from this thematic in order to extract several type of metals.
Thank you.
Yeah, great. Thank you very much, Roma. It would be interesting to hear about that at some point, perhaps, in more detail, this potential of brines. Maybe give us an email if you'd like to give a talk. Marion, do you have another question?
Can I ask a question to the audience? Because this is, I've given this talk quite a few times, and I have a very composite feedback about whether these tiny mineral phases, which can be quite small, like down to 100 microns, can be highly concentrated, are they economically viable to process, even though they can be separated by physical means? They may be too small or not economically viable. So, and every time I ask this question to the audience, I have both answers. Some people say, no, never ever it will be viable to get these, even though it may be a little bit like resource efficient, just to get them out by physical means and not so much hydrometallurgical means. So yes, I'd like some feedback from the audience in case you have any experience or idea about that.
Okay, we'll keep an eye on the answers.
Yeah.
I don't have
feel free to write any feedback for Bénédicte in the chat, and we'll unmute you if you'd like to comment something. While you're thinking, perhaps we go on to another question, Bénédicte, and that is one from, oh yeah, some things coming in there. Okay, some from Lingli Zhao. Sorry about the pronunciation. I am going to unmute you if you would like to ask. 1 moment. Okay, you're unmuted.
Okay, thank you, Alannah, and thank you, Bénédicte, for a very nice talk. Myself is actually working on the lead zinc deposits in the Irish, in Ireland, also look at the germanium. So it's quite interesting to look, to see your perspective from the metamorphic point of view. So I think my first question you actually answered about regarding the source of the germanium. That is also a question bothering me at the moment. So I want to hear your opinions. Well, I think you already answered that, and I can't agree with you. Regarding the tailing, I think it's because I'm also part of my project is also working on tailings. I have some tailing samples. When I look at them, the mineralogy basically totally changed. So I think when you think about that, that may actually affect germanium occurrence.
Thanks for the question. Concerning the tailings, I'd like to refer to a recent presentation with Catherine. We were convening a session at the virtual Goldschmidt 2 or 3 weeks ago about concentration process of rare metals. And there was an abstract from the Sarah Wright from the USGS Geological Survey. And she was looking at germanium in tailings. But as a hard rock geologist, I'm kind of I think in terms of high temperature processes, I wanted to know where the germanium is in the sphalerite from a high temperature, but from a very different point of view. And in my tailings, which sits at the surface thermodynamic condition for a long time, you can have as well as transformation at low temperature. And which was quite interesting in this abstract is that she could find, Sarah could find germanium both in the sphalerite, must be high temperature, and in some hemimorphite, something like that, which are really low temperature minerals and remobilization and recrystallization at really low and surface conditions. So we are kind of how to say, conditioned to think in a way we've been learning and working routinely for years. But if we can get a guideline of looking at the texture, looking at the chemistry and the in situ chemistry, without having this pre-way of thinking in terms of processes, it can help and as well broaden the way we can tackle the problem. So yes, because what's important in the end is where the resources is not only to stick to something or a workflow and approach we are used to use. Does that answer your question?
Yeah, I think it's more like a discussion. There's still a lot of things to discover, to explore.
Yeah.
Thank you.
Thanks. Yeah, Alannah, I think we have a question on YouTube, maybe.
Yes, there's a couple of questions come through on YouTube. So one is from one of our hosts, Aaron Hanche. So he asks, should there be, kind of looking forward, a preference for more on the tailings, so reprocessing of tailings associated with different settings? So I know you looked at the orogenic gold, orogenic type settings, but what about like the magnetic hydrothermal setting for these critical metals and zinc, but what about some others as well? Where would we focus?
I would still answer, go back to the same workflow, is that we need to find, I don't have the right answer, but we need to find a workflow that's independent from the settings. And maybe we'll highlight with time, I'm kind of like now stuck in my way of thinking about recrystallization and texture and chemistry. So this is one way of maybe one red line, which could guide a workflow to process tailings and ores, or not process, but look at in a very general manner for metals in terrains which has suffered metamorphism and orogeny, and there are a lot worldwide. Concerning hydrothermal, to me hydrothermal processes are still magmatic processes and metamorphic processes. So they could be quite a similar approach. And when talking about mineralogy in this kind of rocks, we get down to the bottom line of very classical approaches that we use in petrology, mineralogy, and chemistry. So this could still be taken into the same red guideline.
Okay, yeah, great. I think that's it sounds really key to develop this workflow that could apply to all. So yeah, thanks for stressing that. Marion, do you have another question there?
I don't see a question myself. I have there are a lot of advices and comments. I have a more personal question maybe, and it's on the work that Alexandre has done, Grosjean. So I'm not sure if I followed well. So you reconcentrate the germanium in these deformation structures, but is the indium and gallium following at that point, or where is it going, these elements?
In this very specific case of the Pyrenees, in the recent article we've published like 2 years ago, 2 weeks ago in Mineralium Deposita, we looked at well an indium and gallium, and there is almost nothing.
Yeah, okay.
So there is still a question in this chemical system. So zinc, in this zinc chemical system, there are some deposits in which we are kind of little more enriched in germanium, some more in indium, for example, in the Scandinavian shield, some in gallium. And this is the discussion we had as well in our session at the Goldschmidt. So we still don't understand how these are decoupled. These three elements with zinc affinities seem to be decoupled in each locality. So we haven't quite understood how they work together. Between germanium and gallium, there are some coupled substitution within sphalerite, so they can have kind of correlation, but leading to the formation of germanium minerals or gallium minerals or indium minerals, to my knowledge, we never really found them together. So there is always like the first order ideas, and when you dig into the details, like, okay, what happens? So to me, a general approach, and what I really like to do is like to have first order ideas that can guide us, and then we test. And either we go forward, otherwise we have to rethink our initial idea and strategy, and discuss and have a conversation between the different approaches in order to get some and specific workflows. So
I don't know in terms of processing if it's, I have no idea if it's easy to separate gallium, indium, and germanium, which are in the same, or if it's better to find them in different places so you can separate them differently. I'm just wondering.
They are not usually found in the same place. Maybe some people in the audience may a bit more assertive on that, but even though they all have a zinc affinity, I'm not sure they are extracted the same way in each locality. So there may be some still second order discrepancy or on how these concentrate, or maybe it just depends on the bulk composition at the beginning. I mean, as a metamorphic geologist, I answer every question usually when I teach for any tectonic colleague asking, well, what is this? Oh, it depends on the chemistry. So maybe it just depends on the chemistry of the.
First of all, yeah. Cool, thanks.
I have another question coming here that I can ask. So in terms of looking at these kind of some different settings, I know you had for the orogenic setting, but there's a question here about someone is in an epithermal gold mining company for an intermediate sulfidation type deposit, and they do have a lot of sphalerite, and they wonder, is there any chance of a germanium enrichment in this sphalerite in an island arc type setting? Yeah, do you have any comment there?
I would say that in a general manner, sphalerite is usually concentrated, can have concentration about a few hundreds ppm to a few thousands ppm of germanium. But usually the techniques used in companies, I may be wrong, but as really bulk, so grinding the ore in a general manner and having a bulk chemistry. So it does not represent the processes, it just says this sample has this kind of chemistry. And you don't need much effort and much knowledge and much money to try to locate in a mineralogical manner, not only geochemically, where the resource sits actually, with that, whether it is like in the crystal lattice of salarite, or this is a nugget, or this is an inclusion. It just takes like half a day, a good sample, and a half a day or 1 day imaging at the map and on the laser to locate this resource. And then you can think in from a very different point of view if you want to extract or recover this. So I don't exactly know these settings, but I would first look at texture and in situ chemistry rather than bulk chemistry.
Yeah, okay. Thanks, Bénédicte. That island arc setting, I wonder, like you mentioned there's a affinity of germanium for organic material.
Organic matter, yes, like coal and organic rich metasediments or sediments. Yeah.
Okay. Yeah, I'm not sure myself about that particular setting, but maybe there's something to look into if there is some organic sediments around, if there can be some leaching in the process of those fluids coming up. I'm not sure, but maybe something to look into. Okay, so I have one question myself. You mentioned towards the end there this kind of goal towards attaining this circular economy and involving recycling. And there were a few comments early on in the chat, which I will send to you afterwards, about whether it's kind of feasible to recycle something like germanium, because potentially the lifetimes of the items that we use that in are quite long. So I just wondered, in terms of, especially around these the wind turbines, do you think it's feasible that we can actually get germanium into the recycling process when the wind turbines the lifetimes are so long?
In a general manner, to answer first in a very general manner, I think to my knowledge, the design of the products that we have now on the market are not well designed for being recycled. So often these minerals or these metals are highly diluted, and I'm not sure. Germanium is not such a good example, because, for example, in Australia, germanium has a huge potential in the tailings for zinc. So they may not even be necessary of thinking in terms of recycling for this very specific element. But what I know as well from for example, for the rare earths, they are really highly diluted in the different devices and really low concentration, and separating them one from each other it's quite difficult. So I believe that a strong effort has to be made by the engineers who are building the materials now to think in terms of recycling in 20 or 30 years. We shouldn't think short term. We should really think in terms of like decades to make it better. And I think Olivier Davidal in his YouTube talk presents it really nicely. This is a focus on copper, but which is very important as well. And I guess the different recovery and recycling procedure for all these different metals and in the different materials it's a specialty on its own for engineers and physicists and chemists. So I cannot answer this question directly, but I believe that for germanium specifically, we have so much potential in the wastes and above all in Australia, for example, that it may not be necessary or even economically viable.
Okay, thanks very much, Bénédicte. It's super interesting, and I think that's maybe a good place to wrap up here. I think Marion and I didn't see any more questions coming through there, so I'm looking forward to actually going back and watching your other talk. And it was very interesting to hear about this outlook and the different workflows that we hope to produce in the future. And Marion, do you have any other comments there?
No, I think it's right, and Bénédicte put forward some really good points with mixing the community, and you also advised us to mix that community and our deposit hub. So I think that's where we have to go to. So, yeah, thanks a lot.
Definitely. It seems like this interdisciplinary study in terms of actually attaining a circular economy and producing the critical metals that we need is so important. So thanks very much for highlighting that, Bénédicte.
Yeah, thank you very much. Yeah, thanks for hosting me, and yes.
Yeah, thanks, Bénédicte. So yeah, to keep up with the same thematics, this afternoon or later during your day, we will have Emma Didi. Sorry, I forgot her name. So yeah, join us for this talk this afternoon if you're still awake. And otherwise, thanks a lot, Bénédicte. That was great.
Thank you, and have a nice day or evening or night, everyone. Bye-bye.
Thank you very much. Thank you, everyone, for attending and staying around for the discussion. See you later, hopefully.
Thanks. Bye.